that is not related to programming or C, but to support the compilation process, the Makefile. In the last chapter, we asked an important question. If we do not use function calls such as digital write, pin mode, and so on that are supplied by the Arduino library, why do we still have to use the Arduino IDE? That is a very valid question, and although we do not use those function calls anymore, at the moment we still need it to compile and upload our programs. However, in this lecture, we will write programs without Arduino support, but solely depending on the AVR library. In this session, we will be targeting Makefiles. A Makefile is a tool that helps in compilation processes tremendously. It is a collection of comments, rules, and variables, and once set up, it eases the compilation and handles dependencies. Before ditching the Arduino IDE, there is something that we need to address first. Currently, even the simple blink program consists of two functions, setup and loop. However, according to the C standard, every executable binary needs to have a function called main, which serves as an entry point to start the execution. Libraries are exempted from that rule, and hence they cannot be executed directly. Their functions can be called by another program which is executed and therefore has a main function. So the question is, where is the main? That question will be answered in this session as well. And last but not least, how do we upload our program? In this case, AVRdude is our friend and uploads the hex file into our Atmega MCU. Ready? Let's get started with a Makefile. A Makefile is a file that is clearly structured. It consists of so-called recipes which explain how to compile a program or a part thereof. Makefiles are not only for C programs, but have a large range of applications. For instance, the slides for this video are implemented using the typesetting interpreter LaTeX. The LaTeX source code is compiled directly into a PDF, and I use a Makefile to accomplish this task efficiently. In addition, Makefiles have the capability to check if the source code file is newer than the destination file. If there are no changes to the source file, there is no need to recompile the source file, which can bring an enormous speed up when it comes to the compilation. Makefiles are particularly useful if the compiler chain requires quite a few parameters. Remembering and typing them in can be quite time-consuming. All the required parameters can be comfortably stored in a Makefile and are added whenever they are required. And last, if you start a new project, you can just copy an existing Makefile into your new project folder, adapt the source code file names, and can reuse the entire compiler recipes. So, using a Makefile has lots of advantages, and therefore they are introduced in this session. Not convinced? Let's have a look at an example. The Linux kernel version 3.2 has approximately 15 million lines of code in total. On a normal PC with 4 processors, it takes around 45 minutes to compile the entire kernel with all its modules and drivers to support hardware devices. Imagine a developer changes the source code of the kernel and adds somewhere a new line into the code, which does not have any effect. However, the entire kernel is then recompiled, even the unaffected parts, which will take 45 minutes again. It would be much more convenient if only that part that changes is recompiled. For instance, if the USB subsystem changes, then only these sources and the sources that depend on them are to be recompiled, while for instance the device drivers for the graphical output remain unchanged. The tool that can determine those dependencies and recompile requirements automatically are Makefiles. Interested? Let's have a look at those Makefiles. Let's start with the easiest, comments. In Makefiles, a hash indicates a comment and the entire line following that hash is ignored. Ideal to describe functionality in a Makefile. But comments alone do not get us far. So what else is there? In Makefiles, the most important functionality is defined in rules. Here we can see such a rule. It consists of a target, which is foo.o in blue, prerequisites, which there are two in this case, foo.c and defs.h, and a recipe that describes what to do to get the target. Important here is the tab in front of the recipe. Without a tab, this recipe is not going to work. Let's say foo.c changed. That means that foo.o, the target, needs to be recompiled. The prerequisites define what foo.o depends on. That means if either foo.c or defs.h changes, then foo.o is deemed to be out of date. Same is valid if foo.o does not exist. So once it has been determined that foo.o needs to be recompiled, the question is how to do that. Here the recipe comes into play. Remember, later in the exercises, when you have to implement your own Makefile, to have a tab in front of each of the lines in the recipe. Otherwise, it will not work. So here, to achieve the target foo.o, which depends on foo.c and defs.h, the C compiler with the parameters c and g followed by the source code foo.c is invoked. Note that defs.h is missing in the recipe. We assume that defs.h contains definitions and is included into foo.c. Hence, a change to defs.h might have an impact on the functionality in foo.c. Therefore, this dependency needs to be explicitly expressed in the prerequisites. This is just a small example. Let's build a Makefile for something practical and tasty, the Indian rice dish Biryani. This is how the end product is supposed to look like. It is an Indian dish, very tasty and worth a try. As you can see, the dish contains rice, spices, the white stuff is curd, vegetables and meat in case the non-vegetarian version is preferred. Although this is not a cooking course and I would like to refer you to other courses in case you are interested in the Indian cuisine, with this cooking dish the purpose of the Makefile can be illustrated. And biryani is one of my favorites. So let's start our cooking Makefile. This graph shows the dependencies. As mentioned earlier, we are building a dish and not a library. Hence, we need a main function, which is here in our biryani.c. However, before we can get our biryani, we need to resolve several dependencies. For instance, for this dish, we need rice, that is here, which depends on rice.c and rice.h. Also, the biryani depends on onions, curd, coriander, meat and masala. Once we have all the ingredients ready, we can compile everything into the desired dish. And that is how the Makefile will look like. For instance, to achieve the target biryani, we need biryani.o, which contains our main, plus masala.o, rice.o, onion.o, etc. These prerequisites need to be fulfilled first. Hence, the Makefile will look how to get, for instance, masala.o. That means it checks rules that match the target masala.o and executes its recipe first, similar to rice.o. Since it is the first time that we cook biryani now, rice.o does not exist. Hence, a rule with the recipe rice.o is searched and found. Its recipe is executed to fulfill another prerequisite of our final target. Before we start hacking our biryani Makefile, I would like to point out two further considerations. First, you might have asked, how does the Makefile know that biryani is our final target? It could be masala.o, right? That's a very good question. In general, the first rule that Makefile encounters defines the final target. Hence, Biryani should be the first rule. Secondly, as you can see, every compilation run creates quite a few object files ending with the file extension .o. It is a common notion to provide a target clean in the Makefile that removes all files that have been created during the compilation. In our case, it needs to remove the executable Biryani and all object files created. You can see an example for a rule that has a target clean at the end of the Makefile, right here. One more fact we need to know. What about variables? They also exist and are written like this. First, you define them. For instance, here we create a variable called src containing our source code file sourcecode.c. Throughout the Makefile, we can access the value of the variable by using the name in brackets preceded by $. The spelling of the variable does not need to be in capitals. It is just my personal writing style. In addition, one of the strongest suite of Makefiles are special or automatic variables. For instance, the $sign followed by an @ sign contains the target if used in a recipe. Also, variables for the first prerequisite and all prerequisites are available. This is very convenient, as we will see in a minute or two. Let's head over to our PC and do something practical together. We will start building a Makefile. If you use the image and a virtual machine, you can find all required files in a home directory and then in the folder course Makefile Biryani. In case you do not use the image, you can download the resources. Okay, ready to cook? We first start with the basic Makefile and will optimize it step by step. In the end, a very short Makefile will emerge, which is able to cook our biryani every time and even clean up everything. Let's head over to a terminal and get started. I am already in the aforementioned directory of the VirtualBox image. To create files and to see the content of the files, we need an editor. If you're unfamiliar with Linux, it comes with a few standard editors such as gedit or nano. So you can just type in gedit with the file that you would like to open, or nano. Personally, I'm using the VI in this case, but in the end, it does not matter. I have a Makefile that we already created in class. I also created some source files, such as biryani.c, rice.c, and rice.h, all with a similar content to indicate a dependency to dev.h. Except biryani.c, all of those source files are almost empty. To see the content of the source files, we can use cat of the file that we want to display. This is the content of masala.c, and this is the content of masala.h. Let's try out our Makefile. It is just a short demo. Computers cannot cook, right? So let's try it out. To invoke the Makefile, we use the command make and compile everything. What if an object file is outdated? Let's say the developer changed rice.c. So I open it in the editor and just add a new line to it and save it. Then rice.o and biryani needs to be recompiled. Is that the case? Let's try it out. As you can see, only rice.c is recompiled and not, for instance, coriander.c or curd.c. And the second step, biryani is recreated. First, it is quite cumbersome to add or remove dependencies. The developer has to remember that there are multiple places that need to be modified, such as here and here. And she must not forget the clean rule either at the end of the Makefile and add or remove the objects. So it would be less error prone if all the depending objects are in a single variable. Therefore, let's move them into a variable called object. Objects, and then a list of the .o files. Now I can refer to objects within the Makefile using the $sign and the name, and can remove the remaining of the line. I can do the same here. And obviously in the clean rule. So far, we described all the objects and rules explicitly. However, Makefile is able to deduce some of the rules. For instance, if the prerequisite onion.o is encountered, which is in this variable now, Makefile assumes that the source for this object file is named onion.c, and since it is a C file, the C compiler is used to obtain onion.o. Therefore, we can exploit this assumption and remove all prerequisites for all objects that have the file extension .c, leaving behind the header files if they exist and defs.h. In addition, since even the recipe is assumed by the Makefile, we can remove it. Let's use implicit rules. That means Makefile deduces that onion.o depends on onion.c and the recipe. Therefore, we can remove it, leaving behind defs.h and remove the recipe. As you can see, all objects depend on defs.h, and we have already a variable containing all objects. Hence, the next logical step is to use the variable to express that all objects depend on defs.h. For in few objects, we have header files though, so we have to define them separately. Therefore, we use the variable objects, which is a list of all these O files, and tell Makefile that they all depend on defs.h. Then we can remove these implicit rules. And since rice.o and masala.o is also part of objects, Makefile already knows it depends on defs.h. In addition, it depends on these two header files. That's already pretty neat, but we are not done yet. The issue is the rule clean. If there is a target file called clean, Makefile will get confused as to what to do, either cleaning up the intermediate files or compiling the target file clean. To make sure that clean is not a file target, the keyword .phony is used to avoid any confusion and to declare that clean is a special target that does not create any file. Therefore, we write .phony in front of the rule. Okay, so far so good. What else can be optimized? Remember the special and automatic variables? Have a look at the rule with the target Biryani. It would be nice to avoid double mentioning of the target in the target itself and in the recipe. Using the automatic variable for the target, which is $add, we can rewrite the recipe like this. Let's try it out and let's see if it still works. Save it and execute make clean to remove the intermediate files from the previous compilation run, and make. It still works, but now our Makefile is small, easy to debug, and less error prone. That concludes our cooking session. Now we are able to create our own Makefile. In the next session, we discuss what else is missing to move from the Arduino IDE and to write efficient and power-saving programs. Apart from a Makefile, what else do we need? By now, we know how to develop programs in C, and we know how to compile them. What else is missing? Before we can move on, we have to address the problem that the Arduino, or also called AVR-CPU architecture, is fundamentally different from the processor architecture in your PC. The AVR architecture has a different instruction set, and some instructions that your processor and your PC can execute cannot be executed on the Atmega, and vice versa. So the question is, how can we compile programs for that AVR architecture while running the entire compiler chain on your PC? In addition, we said that every C program needs a main, but in case of Arduino programs, why is it missing? And what shall we include to get, for instance, the addresses for the registers that we introduced in the previous chapter? And last but not least, even if the entire compiler chain works and we successfully created a binary for the AVR architecture, how do we get it into the Atmega? So let us address all those questions, starting from the first one. Usually, and as we have seen in the previous session about the Biryani compilation, we have a compiler collection that is executed on your PC, which creates programs that can run on the same processor. If you have a modern 64-bit processor, the compiler collection consists of programs compiled for the x86 64-bit architecture. That compiler collection is able to convert your source code into instructions for the very same architecture as we have seen earlier. However, if you are, let's say, an app developer and you run the Android IDE on your PC, very rarely battery-operated smartphones have a powerful Intel-compatible processor integrated due to the power constraints. Instead, most of the times, an ARM processor is encountered. Nevertheless, you can write and compile apps on your PC for the ARM processor. Similar, we would like to use the PC to compile programs for the AVR architecture. This method is called cross-compilation. We use the programs of the compiler collection, which is executed on your PC, to create programs for processors that are not in your PC and hence cannot be executed on your PC without an emulator translating all unknown instructions into the instructions your PC CPU understands. Fortunately, since we already installed the Arduino IDE, a cross-compiler is already available. We just have to find it. For that, go to File and Preferences and tick the verbose mode for the compilation. If you compile a program now, there will be tons of messages in the lower part of the screen. Let's try it out. Look for the directory of AVR-GCC or AVR-G++. Either this one or this one. As you can see, it is installed in this directory. Make a note of this directory so that we can use it in a Makefile later. After we figured out where the compiler is, the question is what is required to execute it. Here are a few parameters required, and we go through them step by step. First, we have to specify the MCU that we are using. For the Arduino Uno and Duo Melanove, the ATmega328P is used. Hence, we choose this MCU. There are other MCUs that the AVR-GCC can be used for, such as the ATmega2560 that is integrated into the Arduino Mega, or the tiny ATtiny. The entire list is too long to be mentioned here, so I would like to refer you to this link, which contains a comprehensive list of supported MCUs. The next parameter defines the clock speed in Hertz. The ATmega328P of the Arduino Uno is clocked at 16 MHz, as we already figured out when we measured the number of clock cycles required for the delay function of 1 second. This parameter is equivalent to defining f_CPU 16 million in your code for the preprocessor. This parameter is required to get the timings of the delay function right. Since there is no scheduler, the only time reference that is available in the Atmega is its clock speed. So literally, by counting the number of past clock cycles, it knows how much time has passed. The next parameter, OS, instructs the AVR-GCC to optimize the program for size. We have only 32 KB of program memory, and the entire program needs to squeeze into that space. Since the ATmega328P is just a small processor, a program optimized for speed is secondary. Primarily, the code has to fit. In case you have enough program memory available, you can try out other parameters such as O, O1 or even O2. This parameter instructs the compiler to print out all obscure encounters in the code. For instance, warnings about wrong castings, that is, convert one variable type into another one. It is a good practice to have a look and address them to avoid bugs in your program. If you would like to turn off the warnings, replace this parameter with a lowercase w. The next parameter is not for the compiler, but an instruction for the linker as indicated by the WL. It instructs the linker to remove unused sections from the ELF file. In the earlier chapter about the compiler collection, we had a brief look into the structure of the executable and linkable format. Earlier, we discussed that the entire compiled program is divided into sections containing program code, constants, or variables. If there are sections which are empty, the parameter GC sections removes them, reducing the program size even further. This parameter becomes even more interesting in conjunction with the next two parameters listed below. This instructs the compiler to reserve a section in the ELF for every function in the source code. While this might be unnecessary, many times functions exist but are never called. Hence, the program code is optimized by removing the function. Having every function in a section and with the GC sections parameter for the linker, any function that is not used is removed from the binary. Cool, isn't it? The same is valid for sections that contains variables. If a variable is not used, especially global variables, and if they are in their very own section each, it is quite easy to remove them in the linking stage. That concludes all parameters required for the AVR-GCC. Later, we will create a makefile containing all those parameters so that you do not have to remember all of them. Since we know by now how to cross-compile for our ATmega328P, let's proceed with the next question. In the Arduino program, where is the main function and why aren't there any include directives? Consulting the verbose output and scanning through the files that are compiled by the Arduino IDE, some files stick out. these are the files that are compiled, and later you will see this file. It seems there is a main.cpp that is also part of the compilation. Let's have a look at its content. For that, we open the file in the editor of your choice. In my case, it is VI. I just would like to point out the most important takeaways here. First of all, it seems we found our main. In it, the setup function is called once at the beginning. That is consistent with the setup stage, that is, for instance, configuring the speed of the serial interface, etc. Then, in an endless for loop, without an exit condition, function loop is invoked repeatedly. Also noteworthy is the inclusion of the Arduino.h library. Arduino.h is in the same directory as the main.cpp file. Let's open it and have a look at it. It contains function prototypes of the Arduino library, such as pinout, digital write, digital read, millis, delay, etc. It also includes some essential libraries of the AVR library that is shown here. These files are somewhere hidden in the directory structure of the Arduino IDE. You are encouraged to search for them and to examine the contents to learn more about the AVR library. With all that information extracted from the Arduino IDE, now we are ready to implement our blinking LED example without the usage of the IDE. In the following guided exercise, we will create a Makefile to cross-compile our blinking LED program. This Makefile can then also be used as a foundation to other projects. So let's open a terminal or your favorite editor and get our hands dirty. Please note, the solutions are provided in the resource folder as well. However, to increase the takeaway from this lecture, I'm asking you to try first and to peek at the solutions only if you get stuck somewhere. Alright, have fun in the exercises. See you in a bit. Welcome back. Let's have a look at our to-do list. We did not only answer the question about cross-compilation, but also the whereabouts of the main and includes. Now we have our blinking LED example ready and converted into an Intel hex file format ready to be uploaded. How to do that? For this, we use AVRdude. AVRdude is not only a cool guy, but it also stands for AVR Downloader Uploader. It is basically a tool that first resets the Arduino. The reset forces the Atmega to load the bootloader, which then waits for 2 seconds for a new program. That is the reason why your program does not start immediately, but after a 2 seconds pause after reset. Later in the course, we will remove the bootloader to be able to utilize the entire 32 kilobyte of program memory. That not only saves us 2 seconds startup time, but also 512 bytes of program memory. However, those advantages are paid for by a more uncomfortable programming method. But later more. Right now, the bootloader is doing its job. Back to the AVRdude. What are the most important parameters that we need? First, there is the capital V, which instructs AVRdude not to verify the data written. To be sure, do not use -v. There is no harm in checking if the data has been uploaded properly. In case of weak and cheap USB cables, errors could occur. And if they occur, it might take a long time, since you would assume that there is a bug in your program first. It saves time and just adds a second or two to the entire upload process. The second parameter, capital F, indicates that the signature should not be verified. Usually, AVRdude checks if you upload your program to the right MCU. Different MCUs will have different hardware constraints. However, sometimes, especially in imported Arduinos, another Atmega 328 might be used. There are variations as in Atmega 328P, Atmega 328PU, and Atmega 328 without a P. The differences among those variations are not related to programming. However, in that case, the signature check fails, and you can turn off this check in case you are sure that you specified the correct MCU. This is the part, hence the parameter P. It defines the MCU that you would like to upload your program to. There are several possible part numbers, and I would like to refer you to the complete list under this link to get an overview about the supported parts. The C parameter defines the programmer to be used. Currently, we are using the bootloader and the MCU is programmable through the USB interface. Hence, Arduino is the right choice here. Later, when the bootloader is removed, we have to change the programming method. Later more. "-B instructs AVRdude to send the program at a transfer rate of 57,600 symbols a second, or also called baud. That is the standard speed for the bootloader. "-U is more interesting. It defines what memory is to be programmed. The Atmega 328P has several memories, such as the program memory called flash, and then fuses and EEPROM. Hence, AVRdude can also be used to extract information that has been stored in the EEPROM, such as data from sensors or configuration data. Here, we would like to write, indicated by the W, the file blink.hex containing our blinking program into the flash, the program memory. And last but not least, we have to specify the port where the Arduino is connected to. In Linux, it will be either dev TTY ACM or TTY USB followed by a number. If you try to upload a program and you get an error message such as access denied, ensure that your current user is in a group Dale out. So, with that, we have everything together to adapt our Makefile to include a target upload to allow us to upload the freshly compiled program. Let's head over to our development environment and try it out. In this session, we learned quite a lot. First, we studied Makefiles, their rules, targets, and recipes. And we did not only study them, we directly applied the learned topic and utilized the Makefile to cross-compile our source code for the Atmega MCU. With that, and with the introduction of AVRdude as uploader, we can now ditch the Arduino IDE and write most efficient program code. And higher efficiency means faster execution times and longer battery life. But before going there are some topics that we have to examine first. And that brings us to the next topic of the next session. In C, it is very easy to make mistakes and despite that end up with a running program. However, the flawless program execution is not guaranteed, and we are going to have a look at the most annoying form of bugs. Bugs that are hard to debug since they occur sometimes and only in specific situations and simply vanish if the program is debugged. But later more about that. Stay tuned. See you in the next chapter, and do not forget to do the exercises at the end so you become more comfortable with the new way of programming. Thanks for watching.